parallel resistors. Resistors are said to be in parallel when the voltage across them is the same. That's the basic definition for resistors in parallel. So I want to show you some ways that you can easily identify resistors in parallel, and so that you will not waste time. So let's say they give you a circuit like this. This is how I easily identify my resistors in parallel. So what I do is that, let me say they've given me R1 and R2, and I don't really know. Let's say I don't even know the definition that resistors are said to be in parallel when the voltage across them is the same. Let's assume that I don't know that, and I want to really find out which of these resistors are in parallel. So R1, we have R1 here. Sorry, we have R1 here and we have R2 here. So I want to consider, let's consider this figure first. I want to consider which of them are in parallel. I want to check whether they are in parallel. So basically what I do is that if I start from one terminal, from this point, if I start from one terminal and I'm able to circle the two resistors from one point to the other and back without meeting any third element, that means the resistors are in parallel. So if I'm able to move from this point all over to this point, to this side, and back, and I only meet the two elements, the two resistors that I'm considering that they are in parallel, that means those resistors are in parallel. And since this R1 and R2 are in parallel, I can just denote it as R1 is in parallel with R2. So in some books, this is how you will see it when resistors are in parallel. So further, if we are going on in calculation, when I identify resistors in parallel, this is how I'll write it. So in parallel, we just denote them as this with those two bars. So even in exams, when you do it like that, they will tell you to prove your answers. When you do it like this, they will know that yes, when they are marking, maybe if they want to give you extra point, fine. So for this one too, we'll look at this. So from here, I'll be able to move from here all the way to this resistor, down, all the way to this place, down, back to here, meaning R1 and R2 are also in parallel because I'm able to move, the cycling is working. I'm able to move this from this to this. I didn't encounter any third element. I only encountered the two resistors that I'm considering that they are in parallel. So I can also say from here that R1 is in parallel with R2 in this diagram. So moving on forward, we have a general formula in calculating resistors in parallel. And so since the resistors are in parallel, we have a formula which is 1 over RT. I know that they proved this formula with you in class, and the proving isn't really important here. You should know how to use the formula, that's all. So if you want to know how to prove it too, fine. So we can simplify this as RT is equals to R1 R2 all over R1 plus R2. So this formula can become like this. So this is the total resistance formula, the resistance formula for resistors in parallel. So let's say if there's a third resistor, I can add it, R3 here plus R3. So that is how it is. So I will take a simulation for us to see how it really works. So so this is the formula, as I was saying. This is the formula you will need to do your calculations. So okay, so with the simulation, I think I want to simulate resistors in parallel. So with resistors in parallel, let's look at this. So from here, we realize that the voltage, this is the voltage source. When it delivers the current, when it gets to this node, just from the definition of the node, we know that a node is a point where currents place or divide. So at this point, the current, some splits and some are going to this side, some are going to this side. Then it comes down. So one trick I also want to give it to you guys is that to easily detect whether resistors are in parallel or not, always ask yourself whenever there's a current flowing from the source. Let's say the current starts from here. When it gets to this node, ask yourself, does it have a choice or it has no choice? If it has a choice to choose a direction, that means basically it tells you that there is a parallel there. There's some parallel happening somewhere. Because at this point, if it was in series, it wouldn't have had a choice. It would have just all moved. All the current would have moved and all to one side and all the way back. But at this point, it has a choice either to go to the left or to go to the right. So that is why they say at a junction is a point where currents split or divide. So moving on forward, I think um, at this side too, you come to see that the current here, it gets here, then splits. So let us use our trick, the trick I showed you, to easily see whether we can identify the parallel networks or not. So here when we come, we realize that when we want to circle from this node, we can circle to this resistor all the way back here, then we move back here. We didn't meet any third element, meaning this and this are in parallel. Then we can also circle from all the way here. We move, we move, we move back here. They are also in parallel. This one and this one are also in parallel. Then we can also move from here all the way here down, then back, telling you that this and this are in parallel. So basically, that is the analogy for parallel and parallel circuits. So we'll move on to one of the next important concepts, so that when we understand those concepts, we'll be able to solve questions.